These notes are on complex number on the polar plane. So the first thing I want to do is I want to show how you transform a complex number into its angle and radius components on the polar plane. So you'll remember if I graph this number on the complex plane, -2, so it would be the point -2, 3. And so when I'm transforming this into its polar coordinates, I need two pieces of information. I need its length, the radius, and I need theta, its degree. So the radius is Pythagorean theorem. I make this lovely triangle. I have this as a length of 2, and this is a length of 3. And so my radius is the square root of 2 squared plus 3 squared, which is the square root of 13. For my theta, I'm looking for this angle. And if you remember, the other thing to remember is that this point also signifies d cosine theta, or we'll call it r, excuse me, r cosine theta, r sine theta. And so I now know what r is, so I can set up an equation that can allow me to find theta. But the other thing that we know is that tan of theta, and we're going to call it theta 1, because I'm actually finding this theta. So remember, tan is opposite over hypotenuse, so tan of theta is 2/3. So theta 1 is going to be tan inverse of 2/3, which means theta 1 is approximately -0.059. But if you remember, I was actually trying to find this angle, and so I have to actually add pi to that. So theta is going to be approximately theta 1 plus pi, which is approximately 2.55. So I now can turn this complex number, so any complex number, a plus bi, is equivalent to r times cosine theta plus I sine theta. And so in this case, we have root 13, comma, cosine 2.55 plus I sine 2.55. And it turns out that if I actually simplified this, I actually would get 3 plus 2i. I could put these numbers into my calculator, and that is what I would get. So now there are several operations we do with these complex numbers in the polar plane. So the first one we're going to do is we're going to multiply two complex numbers. And so we have some formulas for this. It turns out that once I have multiplied, turned this into its polar coordinates, and then multiplied it all out, I end up with R1 times R2 times the quantity cosine theta 1 plus theta 2, I sine theta 1 plus theta 2. And so it's kind of this nice connection between when I'm multiplying complex numbers, I'm multiplying their distances, but then I'm doing the sine and cosine of the addition of their angles. So for example, we can take 1 plus 2i and 4 minus 3i, and we can change that into our r1 being square root of 5, our r2 being root 5. Tan of theta 1 equals 2/1, so that means theta 1 is approximately 1.11. Tan of theta 2 equals -3/4, and so that means theta 2 is approximately -0.064. And so now I can take these numbers and plug them into my formula. So we call them z1 times z2, my two complex numbers being multiplied, are going to be 5 root 5 times cosine of 0.47 plus I sine of 0.47. So that's how I can multiply two complex numbers. And it turns out, again, if I simplified all of this, I would actually end up with, this should be an approximate. I should end up with approximately 9.97 plus 5.06i. Let's multiply these out the old-fashioned way. The old-fashioned way would get me 1 minus 3i plus 8i minus 6i squared, 4, excuse me, which is going to be 4 plus 6 plus 5i, which is 10 plus 5i. And we can see that our approximate is very close to our exact answer here. The other thing I can do with complex numbers is I can divide them using the polar coordinates. I'm not going to do an example of that, but I do want to show you that if I am dividing two complex numbers, the formula is very similar to the one we just saw for multiplying complex numbers, except that I divide my, my radius and I subtract my angles, which does sort of make some intuitive sense in terms of the way it works when we're dividing numbers with the same with different exponents but the same base, and kind of makes sense in terms of some of the math that we have seen prior. The last thing that they often have you looking at when you're talking about complex numbers in the polar plane is raising a complex number to a power. So in class you discovered that the formula for that was r to the n cosine n times theta plus I r to the n sine n times theta. Sorry about that, give me 1 second. I apologize for that tiny glitch. So now if we do an example of this, I'm going to take a relatively straightforward example because I would like to be able to verify it. So if I have -4 plus 3i to the third power, I know that my r is going to be the square root of 25, which is 5. Tan theta is going to equal -3/4, which means theta is going to be approximately 143. I then can say that this is 5 to the third, cosine of 3 times 143, plus I, 5 to the third, sine 3 times 143. And when I simplify that all out, I get, this is a little side note, I get approximately 45 plus 117i. So now let's verify this. Let's see what happens when I have -4 plus 3i cubed. That's going to be -4 plus 3i times -4 plus 3i times -4 plus 3i. Multiplying the first two, I'm going to get 7 minus 24i. You can verify that on your own. And when I multiply both of those, I get 44 plus 117i, which is approximately the same answer that I got above. This becomes really powerful when I have complex numbers to really big roots. Because remember, I only had to do this 3 times, but if this were the 10th, verifying that would mean I'd have to do -4 plus 3i times -4 plus 3i times -4 plus 3i 10 times, which starts to become a little bit much. And so transforming them into their polar coordinates allows us to perform the multiplication and the powers much more quickly.